Okay, this next one is a proof problem. So let me show you which one it is. Number 9, show A and A transpose have the same characteristic polynomial. So I'm just going to prove that statement. And I think they guide you through these proofs step by step. I would probably do the same thing on a test if I put one of these on the test. I wouldn't make you prove the whole thing by yourself. I'd make it step by step if I did that. But I kind of like to do some of these all in one shot. All right, let lambda be an eigenvalue of A. Then we know that means by definition there exists a non-zero vector that satisfies the equation A minus lambda I times x equals 0. Okay. And we know to get the characteristic polynomial, we just have to take the determinant of that matrix. So that is the characteristic polynomial of A. Now let's do the same thing for A transpose. We'll let lambda be an eigenvalue of A transpose then we know there exists an x not equal to 0 such that A transpose minus lambda I times x equals 0. Thus, the determinant of that matrix is the characteristic polynomial of A transpose. Okay, so we really just have to show that those two polynomials are the same, and they certainly don't look the same right now, but they actually are. So we must show that the determinant of A minus lambda I is equal to the determinant of A transpose minus lambda I. All right. Now here's the key observation, or one of them. When you subtract lambda I from a matrix, it only affects the diagonal elements. So that's not going to affect the determinant when you take the transpose of it, or when you take the transpose of that matrix and find the determinant after that. And let me be a little more specific. If you consider A minus lambda I transpose, so notice we're going to subtract lambda I from A first, and then we're going to take the transpose of that. Well, that's the same thing, believe it or not, as this, A transpose minus lambda I. Okay, and I might just pause there just to give you an example to maybe argue about why that's true, or to convince you that that's true. I'm going to pause the proof just for a second and just kind of give you an example. Okay, let's just say we start off with a matrix 1, 2, 3, 4. I'm just pausing to convince you that that's true. Well, A minus lambda I, in this case, is 1 minus lambda 2, 3, and 4 minus lambda. Okay? Now, if you take the transpose of that, I'm just going to show you it's true for an example, just to convince you. Well, it's not going to affect the diagonal elements at all. So the first row becomes the first column, and the second row becomes the second column. So notice the main diagonal elements did not move at all. So this is really the same thing as the transpose of A minus lambda I. Okay? Because if you took A and you formed the transpose of it, and I guess I'll do that down here, that would just be this matrix. And if you subtract lambda I from it, you're going to get this guy. Okay? So it certainly seems to be true for this particular example, my statement, that this is equal to this. But it's actually true in general, and it really has to do with the fact that that when you subtract lambda I from any determinant, or matrix, I should say, it only affects the main diagonal elements. And when you take the transpose of a matrix, the main diagonal elements don't move at all. They stay exactly where they are. Okay, so just kind of a side example to convince you that that's true. So let's go back to the proof. So that's true in general. But here I need to give you another fact that you're just going to have to believe. Well, the determinant of A is equal to the determinant of A transpose. And that's assuming A is a square matrix. That's just a fact that I'm going to pull out of the air. I kind of need to use that fact. But that's just one of the properties of matrices and determinants. You can show that the determinant of the transpose of a square matrix is the same thing as the determinant of the original matrix. Okay? Now, combining both of those statements, and let's just pause to think for a second here. We're trying to show that this is true. And I showed that that this, well, let me just think about it for a second. Actually, this and this obviously are the same thing, but I just showed that this is the same as this, and since these two matrices are the same, this has got to be the same thing as the determinant of this. And that's really what I was trying to show right here, okay? So all of those statements imply what I was trying to show, which is this. So you can kind of stare at that a little bit if you want to, but remember, we were trying to show that this is true to complete the proof. So what I'm saying is, take a look at this. These two, the left-hand side of the equation is the same thing as this. I just showed that that's equal to the determinant of A minus lambda I transpose. But since this matrix is the same as this matrix, and that's equal to this, that means that this is the same thing as the determinant of A transpose minus lambda I. And that's what I was trying to show up here. So that's the proof.